Okay, so today we're going to deal with more trigonometric word problems. So in other words, we're going to look at more examples where we use trigonometry to model real-world situations. Let's get going. So today's plan is, like I said, we're going to take one more look at solving word problems using trigonometric functions today. A key idea is determining when it's ideal to use sine versus cosine. There is an advantage to using sine in certain situations. There's an advantage to using cosine in other situations. Really, it all comes down to personal preference. You can use either one. They are interchangeable, but there are times where it'd be better to use one versus the other. It just saves you some time. You'll also need to be able to interpret data about trigonometric functions from graphs. We'll get into that today as well. I want today to be as much as possible like a you try, I go over kind of day. So each time I pose a question, it would probably be for the best if you gave it a try first and then watched as I went over it. Anyway, let's get going. So first things first, let me read this one. Electric current example. In some Caribbean countries, electric current makes 50 complete cycles every second. Of course, if you're not aware, with electric current, it goes from positive, like a positive voltage to a negative voltage. We call that alternating current. Anyway, it is what it is. And the voltage is modeled by V of t equals 170 sine 100 pi t. Use your graphing calculator to graph this voltage over 2 cycles. Use the window settings given. That's in that box there on the side. What do the scales on the x and y axes mean in this case? And then the other two questions: what is the period of the current in these countries? And number or letter C here, what or how many times does the voltage reach positive 110 volts within the first second? If you could pause the video here and give those 3 questions a try, that would be great, and I'll go over it in a second. Alrighty, so question A here. Probably not a huge surprise to most of you, but just in case you're still a little confused, the scales on the x and the y axes, well, x in this case would be our time. So in terms of our x direction, that would just be our time in seconds. Not a huge surprise there. As for the scale on the y axis, that would just be our voltage. And as silly as this is to say, it's in volts, right? Again, kind of a weird question. So x is just your time. And y would be your voltage. Now, B is a little bit more of a tricky question. What is the period of the current in these countries? You can get the period in a couple different ways here. Remember, the period is just how long it takes to complete one cycle. We can see that we have 50 complete cycles every second. So logically, if there's 50 cycles in 1 second, then in 1/50th of a second, you'd have a complete cycle. So right there, that'd be the period, 1/50th of a second. But just to prove it to you, you can also use your B value. Just remember the period. The period can be found by saying 2 pi over b. Well, we actually know what the b value is in this case, so I'm going to say period, I'll just call it p, equals 2 pi over 100 pi. The pi's would clearly cancel out. We'd be left with 2 over 100. Well, 2 over 100, of course, simplifies to 1 over 50. So the period of the current in these countries is 1 over 50. And sometimes it's nice to have period with a unit on it. So I'd say that's 1 over 50 seconds. Right? So that's how long it takes for one complete cycle to happen. So for the electricity to bounce all the way up to positive and then all the way to negative and get back to its starting point, it takes 1/50th of a second in those countries. Question C, how many times does the voltage reach 110 volts within the first second? If you were really crazy, you could have like tried to punch this into your graphing calculator and then set your X max to 1 full second and then counted it. But that would have taken forever. We can use just a little bit of intuition and logic on this one. We know it completes 1 full cycle in a 50th of a second. So 1 full cycle will look something like this. Now, if that's 1 full cycle, notice how our D value in this case is plus 0. That means our midline of our graph is just 0. So the midline is just our x-axis. 110 volts is probably somewhere up here, right? That probably represents about 110 volts. If you look at just one cycle, which again is 1/50th of a second long, you can see we're going to hit 110 volts twice. So it's 2 times in one cycle. But in 1 full second, we have 50 complete cycles. So if it's 50 complete cycles and we hit it 2 times per cycle, well, that just logically means we'll have 100 times that we're going to hit 110 volts within the first second. So a bit of a weird one. We haven't done anything like that quite yet before, but it's more or less just using a bit of intuition and understanding what the shape of a trig graph looks like in order to figure that one out. Anyway, moving on. All right, so this one is a Ferris wheel example. This is a little bit more similar to some of the ones we've done before. So the following graph shows the height h in meters above the ground over time t in seconds that it takes a Ferris wheel to make 1 complete revolution. Well, actually, I'd say that this graph shows 2 complete revolutions, but it is what it is. Notice how it starts at the bottom and then it goes to the bottom here. Anyway, that's me just being, whatever, right? So the maximum height of the Ferris wheel is 19 meters. That would be up here. That's 19 meters. And the minimum height is 1 meter. So it must be like the bottom chair or whatever is 1 meter off the ground when it comes around, right? So the first part of the question says, what is the period for 1 revolution of the Ferris wheel? Now, I'll be honest, this graph might be a little hard to see depending on your screen. I don't know how it looks in your notes off the top of my head. But remember, the period is just how long it takes for 1 full cycle to happen. Notice at a time of 0, we are starting down at the bottom. So that means our period would be wherever we're down at the next bottom here, which would be, by the looks of it, 32 seconds. So I'm just going to write that in, 32 seconds. That would be our period. Question B, how high is the hub or the center of the Ferris wheel off the ground? Well, the hub of the Ferris wheel would be, like it says, the center of this whole thing. So that would be indicating our midline. Remember, the midline is basically the average between your maximum and your minimum. Well, average can just be found by adding them together and dividing by 2. So I'll take my max plus my min divided by 2. That's going to give me my midline. And that would be 20 divided by 2, which of course is 10. So I would say 10 meters. That would be the center of our Ferris wheel here. Before I move on, of course, if we have 10 meters as our center, notice we're going 9 meters below it and 9 meters above. That would be our amplitude, right? So we can also say, hey, we know our amplitude is 9 in this case. That might be useful. I totally forgot to mention, you could have paused the video and gone over this. Obviously, my brain's not in the right place today, but it is what it is. You can also just watch if you want. Anyway, these ones, this next one especially, write an equation for the height of the Ferris wheel. This is one that you're probably going to want to try on your own, for sure. So definitely pause the video here, give this one a shot. All right, so I'm going to go over this one now. Notice how it says we can use either sine or cosine. That's really nice. It gives us some flexibility there, and it gets us to think about which one would be better to use. Well, sine usually starts at your midline going up. And by starts, I mean like at a time of 0 seconds, you'd have your midline going up. This one clearly is not starting at our midline going up. It's actually starting at a minimum. Well, cosine usually starts at a maximum. So by the looks of it, it's like, oh, wait, there's nothing really we can do here. It doesn't start at a midline going up and it doesn't start at a maximum. But here's how I'd get around that. This one starting at a minimum is actually pretty useful because that's just like a flipped upside down cosine graph. So if we have a negative cosine graph, that's going to flip the whole thing upside down and we'll actually start at a minimum point instead. So I think I'm going to use cosine for this one and I'm just going to make it negative so it flips it upside down. You could use positive cosine and then you just moved it over like probably 16 units or whatever. Like you moved it to the right by 16, that works as well. You could use positive sine, and I think you'd have to move it over by about 8. It's up to you entirely. Like there's so many different possible ways you could stitch this together. It is what it is, but I'm just going to use negative cosine. So here's what I'm going to start with. I'm going to say h, that's our y value here, that's our height, equals, we need to start with an amplitude, right? Because remember, it's always like y equals a sine b x minus c plus d. We need to find our amplitude first, right? And sine, cosine, same idea, right? So for our amplitude is just how far above the midline we are. We actually found that on the last graph. We knew our midline is 10. That tells us because we're going up to 19 that our amplitude must be 9. So I'm going to have negative 9, because remember I said I'm using negative cosine to start at a min. Negative 9 cosine, square bracket now. Ooh, now we need our b value. So the b value is, in my opinion, always the trickiest thing to find. You need to use the period to find the b value. So just don't mind me. I'm going to go down here. I'm going to do my work here. I know my period is 32 seconds. Well, period always equals 2 pi over the b value. A little bit of algebra on this. If I move b over by multiplying it over and then divide by 32, I have b equals 2 pi over 32. But I can clean that up. 2 and 32, we can simplify that just to 1 pi over 16, just by dividing both of those by 2. So my b value is going to be pi over 16. I'm going to put that up front here as well. Just an FYI, and we might actually need this in a bit. Sometimes it's nice when you have a weird b value like this, like a b value that's a fraction. Sometimes it's nice just to give it its own set of little brackets just around it alone. You don't have to by any means, but when you punch in your calculator, it certainly makes things a lot easier. Anyway, next thing would be our x. So I'll say instead of x, of course, this is a function of time. So t is going to be like our x here. So time. Now, minus c is like our phase shift. It moves it left or right. But because I use negative cosine, that's going to make us start at our minimum. So I don't need to move this thing left or right. So I'm just going to end that t right there, and that's all well and good. Last thing I got to throw in here is the d value. That's your midline. We found that on the last slide as well. That's just going to be plus 10. So many different ways of putting this together. Like again, if you used sine, you would have had to move it over by 8 because that's where our midline going up is, right? So if you moved it right 8, so if you had t minus 8, that would work for a positive sign. A negative sign, I would bet you probably would have to move it left 8. I guess I'm more visual. I'd need to see the rest of this graph, but I think you'd move it left 8. If you use positive cosine, you'd have to move it right 16. There's a lot of different things you could have done with this, but I think this way that I did it is probably the most clean. That's just my personal opinion, though. It is what it is. Anyway, next couple here, using that formula that we put together in part C, you can answer both of these next questions. Question E is interesting, though, because we're solving for a time. So it's like we're digging out a t here. You're really going to want to use your graphing calculator, like the actual graph function in your graphing calculator to solve E. Pause the video here, see if you can get both of those. All right, so I'm going to go over each one real quick. D goes a little bit quicker. You just have to plug in 10 seconds into that formula that we wrote on the other slide, right? I'm not going to write the formula down again. You can just plug it in. But one thing I will tell you is make sure you are in radian mode. And also, if I just bounce back, when you throw this in your calculator, putting this b value in brackets really helps. Because if you don't, you might end up going pi divided by 16 times 10, when you want it pi over 16 times 10, right? You don't want to divide by 16 times 10, if that makes sense. Anyway, moving on. Anyway, long story short, when you punch this in your calculator, you should get h equals to the nearest tenth 13.4 meters, which I mean, even if you look at this like just visually, 10 seconds is here. If you follow that up, yeah, that looks about right, somewhere around there. I didn't do a perfectly straight line, but you get the idea. Around 13.4 meters, the math checks out. Question E, on the other hand, using a graphing calculator, find the first time to the nearest tenth of a second, the point in the point on the Ferris wheel is 6 meters above the ground. Here's what I did. I reset my window to something a little bit better. My X window, I set it as an X min of 0, an X max of 32, because I know I don't have to go any further than that. And then I just set my X scale to 1, because why not? As for my Y scale, I set it from 0 to 20. That just gave me a little bit of wiggle room, because the top here, of course, is 19, and also the scale of 1. In Y1, I threw that equation that we had on the last slide. Be very, very, very careful. I know I've said this like 3 times now, but putting your B value in brackets in itself, that's a really good idea, right? You don't want to put your variable like right next to that thing without brackets. It's going to really mess things up. So use that in brackets there. It will really help you. As for Y2, though, we're looking for where the first time that we have the Ferris wheel is 6 meters above ground. So we're looking for like this point right here. So for Y2, I said 6, right? Because that's going to draw a horizontal line at 6 meters. Just like that, right? What I did from there was if I go second, trace, and then intersect, that lets me actually find the intersection between these graphs, and I just focused in on this point. So in my window, I only could see like this, right? And I was just looking for this intersection point. Long story short, what I found was t equals to the nearest tenth 5.7 seconds, right? Even like visually, you can kind of see that here as well. It is what it is, right? I don't know. Long story short, that's how we do it. One last example here. All right, so a nail is caught in the tread of a rotating tire at point N in the following sketch. The tire has a diameter of 50 centimeters and rotates at 10 revolutions per minute. After 4.5 seconds, the nail touches the ground. Interesting. Determine an equation for the height of the nail as a function of time in this form. Notice how it wants us to use sine here. It also wants a to be a positive number. I'm gonna let you guys pause the video here. Give this one a try, and I'll go over it in just a second. Okay, so notice how there's only 3 things that we need here. We need an A, a B, and a D. Now it is telling us A needs to be positive. That's a good thing because this already started at a midline going up. So like, of course, A would be positive. Why would we make it negative? It only makes sense, right? So it already starts at a midline going up. That also explains why we don't have a C value in here. We're not moving it left or right. It is what it is. So long story short, we know the diameter of this tire is 50 centimeters. That means if a nail is caught in the tire, the lowest it's going to be is at 0 when it's literally touching the ground. The highest it's going to be, though, is that full diameter of the tire. So I can tell you right now on this graph that this highest peak here is going to be 50 centimeters. Now, in this repeating pattern, your midline, of course, is just going to be between 0 and 50. I don't know if we even need to use a calculator on that one. The number between 0 and 50, of course, is 25. So I know my D value is 25. And since that's 25, remember your A value is how far you are between your midline and your max. That actually coincidentally is also going to be 25. So really, we just now found A and D is 25. Now we just need B. B is always the trickiest part here. There's a couple different ways you could do this. I think the easiest way to do this in this question is to use the fact that we know that there's 10 revolutions in 1 minute. The period tells you how long it takes for one revolution to happen. Well, if 10 revolutions happen in a minute, which is 60 seconds, then one revolution, logically speaking, by dividing by 10 here, would happen in 6 seconds. So 10 revolutions in a minute, that means one revolution would happen in 6 seconds. That right there is your period. That's how long it takes, right? So period, just to use this formula again, is equal to 2 pi divided by b. Well, we know our period is 6, so we can say 6 equals 2 pi over b. And then multiply by b and divide by 6, and we're going to have b equals 2 pi over 6. Let's be real here, though, that just simplifies to pi over 3. Now, another way you could have gotten this, and it's a little bit tricky, but it did tell us that after 4.5 seconds, the nail touches the ground. That'd be right here, 4.5 seconds. Now, this is what's really strange about this. The period would be how long it takes to get back to that full cycle. Well, let me put it this way. In a full cycle, we'll have our midline going up, our maximum, our midline going down, a minimum, and then the midline going up again. So if you break that into like little chunks, you can see that there's actually 1, 2, 3, 4 different segments that occur within a full period. So again, this segment going up, this segment going down even further, and then going back up to your midline. Because there are 4 different segments here, you can say that each of these segments from this point behind is just 1/3 of it. Well, that tells you that this, of course, 1/3 of 4.5 would be 1.5 seconds, which would mean after another 1.5 seconds, we're at 3.0 seconds. After another 1.5, you'd be at 4.5 seconds. And then after another 1.5, you'd be at 6.0 seconds. That is, in my opinion, a way more confusing way of solving for this. It even just told us 10 revolutions per minute. We're good, right? Anyway, long story short, I'm just rambling there. To throw this together, h of t equals a, which we determined as 25. That's our amplitude, right? So 25 sine b, that was a hard thing to find. That's pi over 3 times t. And then plus d is 25. And again, maybe you want to put like brackets around the pi over 3 just to keep that nice and safe in case we have to put it in our graphing calculator. Whew. All right, one last question here. How far to the nearest tenth of a centimeter is the nail above the ground after 6.5 seconds? This is just a matter of taking 6.5 and plugging it straight into this equation right here. So you're just plugging 6.5 into this. I'll even just do that real quick. Literally, it's just going to be h equals to the nearest tenth. I think it's actually an exact number here, 37.5 seconds. Oh, sorry, centimeters, my mistake. 37.5 centimeters. That's about it. So I just put 6.5 into that equation we generated. Awesome, right? That's it. Relatively quick lesson today. So for practice, you can either complete those textbook questions, or let's be real here, we probably want to finish off our chapter 5 assignment. Your work's cut out for you. If you have any questions, please let me know.